Welcome to the UEI Technical Masterclass. I hope everyone's doing well today and weathering this current pandemic. I'm Bob Finn with UEI, and today's webinar is entitled Understanding the MIL-STD-1553 Bus Monitor. This is a continuation of our previous MIL-STD-1553 Masterclass from April 16th. While that particular one was an introduction to UEI's 1553 offerings, in this webinar, we'll dive deeper into the details of the bus monitor. This is not only a presentation of technical information, but an opportunity for you to interact with our application engineering team. Just fire off any questions you have using the webinar chat tool. And please don't be shy. And speaking of our application engineering team, let me introduce them. From the top, we have Timur, who wants everyone to, quote, live dangerously by using the auto set button. Next, we have Austin. Austin's a seasoned application engineer with an expertise in embedded devices. He's also an avid hiker and a bad flight simulator pilot. Moving down the list, we have Brian, who believes every question is a good question, followed by Phil, who will be presenting today's webinar. Phil wants everyone to know he agrees with Brian. Knowledge starts with the first question. And rounding out our roster of application engineers is Prabhu, joining us from the UK. He specializes in solutions, workarounds, and fixes. His mantra, keep calm and carry on. So that's our team of experts. And as I just mentioned, Phil will be reviewing the concepts this morning. So take it away, Phil.
Thank you very much for joining us today. We'll be talking about the MIL-STD-1553 bus monitor. You'll be seeing C and LabVIEW run a complete 1553 application. We support all of our I/O boards with many programming languages and interfaces. I mentioned C and LabVIEW. There's Python, C++, Simulink, and more. We've planned other sessions on 1553, one on the bus controller and one on RTSAs, along with optional event notification and error injection. If you'd like to see something specific, be it a collection of I/O boards or sensors, please chat us or email us. We welcome all of your input. So I've prepared some introductory slides just to go over the general concepts. We have a 1553 system, and on the left is the bus controller, which would be the mission computer, and it's connected to remote terminals, up to 32. Each remote terminal has subaddresses, up to 32 subaddresses. And then there's the bus monitor. The mission computer could be talking to one of the remote terminals, and the best example I have is the remote terminal is a missile launcher, and inside are 32 missiles, so each missile is a subaddress. The bus monitor can look at the data and the commands going back and forth on either side of the bus. 1553 requires a dual redundant bus. This is for safety and reliability. You can configure the bus monitor to look at one side of the bus or the other, or both. The bus controller sends a message on one side of the bus and waits for a reply. If it doesn't get a reply, it tries the other side of the bus. Let's take a look at some of the words you might see when you look at the bus monitor data. The bus controller will send a command word. This command word has 16 bits, and embedded in it is the remote terminal number, the subaddress, the word count, and a bit to indicate transmit or receive. The data word has 16 bits, and the RT replies with a status word. So the RT will reply with a status word with the terminal address in the upper 5 bits, and hopefully with the message error bit clear. So the bus controller knows there was no issue processing the command. Let's take a look at a couple of the basic commands. We support all 1553 commands, but I'll do a subset here. The bus controller needs to send data to an RT, maybe a firing sequence to the missile. So that's a BC to RT command. The BC sends a receive command to the RTSA, followed by data words, up to 32 16-bit data words. And then for reliability, the RT will always send back a status word. So here's the actual bus monitor data from that transaction. You'll see this is the command. And here are the data words. and here's the status reply. Certainly the message error bit is clear, and this decodes to the RT that sent it. We also have this 84, 83, and these numbers here. They're the number of clock ticks between this word and the last word. The data at the end is a timestamp for the message. This is optional. I'll show you how to configure this or not. So this command actually decodes to RT8, receive transmit bit, SA8, 4 data words. Now sometimes the BC may need information from an instrument, so it will perform what's called an RT to BC command. The BC sends a transmit command, and the RT sends a status word and appropriate data words. If we dissect what happened on the bus, you'll see the RT to BC command, the status word come back, and the data words. 4504 decodes to RT8, transmit SA8 4 words. Now sometimes the bus controller needs 2 RTs to communicate together, so it sends a combination of what I just discussed. It sends a BC to RT command, a receive command, which is right here, and one RT is ready to receive something. But then it tells another RT to transmit it. So you'll see on the bus the receive, the transmit command, the RT sends status, which is normal, and all the data words requested. And the second RT that receives the data sends status. So this is an RT to RT command. Let's see what it takes to add a bus monitor to your C code. Here it is. It's a few lines to set it up, and it's 1 line to use it. Here's how you can configure it to listen to channel bus A or bus B or both. Timestamp is optional. Flags are optional. Flags will indicate what side of the bus the message came in on. And now let's take a look at a video that provides an online resource for the decoding of the bus monitor data.
This video assumes that you've collected raw data from the 1553 bus monitor and wish to understand what each word means. Since the command is one of the most important things in the bus monitor data, let's start there. This is the command, and it's an RT to BC command, RT8, SA8, 3 data words. These are the data words, and this is the number of clock ticks from the last word. To convert clock ticks to microseconds, just use the following formula. This represents the fact that the I/O board has seen the bus idle. This is the timestamp at the beginning of the message. This is the timestamp at the end of the message. These are status words, and this is the flag word. One actually indicates the message came in on bus A.
Now that we've played that, I'd like to mention that the I/O board has 2 independent channels. They're complete 1553 systems. Each channel can be wired onto the same 1553 bus or completely independent 1553 buses. Let's see the configuration options for the channels when using a bus monitor.
Many times application development benefits from monitoring or recording traffic on a 1553 bus. A very common solution is to use an external bus monitor. However, when you're using UEI to emulate a bus controller or RTSAs, you can simply add in a bus monitor to the channel that you're using for emulation. Also, since each 1553 I/O board has 2 completely independent channels, you could use one channel for emulation and the other for the bus monitor. Or both channels for emulation and bus monitors. So you can reduce costs by not purchasing the external bus monitor.
Now let's run some code. Our PowerDNA release is available on our website. You can download it for free and comes with all the sample code for all our I/O boards. And for 1553, there's quite a lot. There's samples that cover the RTs, the bus controller, error injection, and standard 1553, which we're going to run today. This is sample 553, and it's designed to be a complete 1553 application run using our loopback dongle. So we've tied channel 0 to channel 1. And I'm going to run it. And we see that the bus monitor is looking at channel 1. The bus controller sent a receive command and then sent a transmit command. So here's the receive command in the bus monitor data, the words associated with that receive command, and a status sent back by the RT. Here's the transmit command, and we expect to see status from the RT and the data words. So now let's move the bus monitor onto the other channel. So I'm going to move this one flag. I'll move the configuration associated with the bus monitor, run it again on this channel, and then have the read call for the bus monitor point to the RT channel now. And that's it. The bus monitor now should be reading channel 0. And here you have it, the same application, the same receive command, same transmit command, same bus monitor data is now being read on channel 0. And it's just that easy. Now that you've seen C code run an application, let's see LabVIEW run the same application.
We've designed our data acquisition and control hardware to be software flexible. That means you can use a variety of different computer languages and programs with the UEI I/O boards. One particularly popular choice among engineers is National Instruments LabVIEW. Let me show you how easy it is to use. The UEI 1553 I/O board has 2 complete 1553 systems. Each channel is a complete system and can be a bus controller, any or all RTSAs, a bus monitor, a combination of bus controller and bus monitor, or a combination of RTSAs and a bus monitor. This is the front panel. And we can take a look at the block diagram now. And we notice that there are UEI VIs ready to go, including one that allows you to select from any of the 3 major 1553 components. Here is a list of the wide variety of VIs and utility VIs that you have access to. For example, we support a major-minor frame scheduler that allows you to send many different types of commands at varying frequencies. So let's exercise a complete 1553 system. I will set the RTSA, word count, and hit send. Now let's take a look at the bus monitor data. It's just that simple. Not only do we support 1553, but UEI data acquisition equipment can interface to a wide variety of inputs and sensors, as well as other avionic and messaging protocols. We supply a library of samples for all these inputs and outputs, so you can create a standard acquisition application. The architecture of our data acquisition system makes it incredibly easy to obtain data from multiple inputs at the same time. and our extensive collection of pre-built examples and VIs really make it easy to get up and running quickly.
Like C code, it's very easy to add and use a bus monitor in LabVIEW. Now let's troubleshoot a system. What if expected commands are not appearing on the bus? Maybe it's a wiring issue or termination issue, something's fallen off the wiring. We can use the bus monitor to see the actual commands the application is telling the BC to transmit.
Troubleshooting your 1553 system. The self-test features of the UEI 1553 I/O board allow you to quickly verify board functionality and move on to isolating other components in your system. You can simply test one channel by writing commands and looking at the bus monitor data with no external connections. We read the bus monitor data at the output pins, so what you see in this test is exactly what will be transmitted onto the bus. Alternately, each I/O board has two channels. The loopback test adapter wires side A and B from channel 0 to side A and B on channel 1. So you can send commands from one channel to the other to verify that both channels are functioning properly. Let's take a look at this in action. In this example, I've set up PowerDNA Explorer to send data from one channel to another. And in this example, without any connections, wires, or connectors, here's PowerDNA Explorer looking at the data from a single channel test. There you have it, a simple way for you to self-test a UEI 1553 I/O board.
The loopback test adapter allows you to debug a complete 1553 application, eliminating all external wiring. This makes debugging portable and eliminates or identifies the wiring as a cause. Also, the design of the FPGA has the bus monitor monitoring the output pins of the bus controller. So without any external wiring, you can verify that the application is requesting the complete list of required commands. But what if some words are missing? The raw mode of our bus monitor allows you to see what's on the bus, whether it's a complete message or not. Let's take a look at that video.
UEI supports all three major components of a 1553 system: the bus controller, any and all RTSAs, and the bus monitor. 1553 is a message-based protocol with commands, data words, and replies. But what happens when you do not get a complete message? How can you tell what words are missing? With the UEI 1553 bus monitor, simply use the read FIFO all flag, and the bus monitor will return to your application any and all words read from the bus, even if they're partial messages.
And just to recap, to enable the raw mode, you simply add one flag to one API call. The result is a complete view into every word, not just every message, on the bus. Many applications simply need to record the bus monitor data. You can always write code in your application to save data to disk, but we've provided a complete bus recorder sample.
Many times, applications require the recording of some or all traffic on a 1553 bus for playback or debugging. UEI provides you with a commercial off-the-shelf product for this functionality in our 1553 I/O board. This allows you to focus on your application rather than engineering a 1553 system yourself. Our board comes with two complete independent 1553 systems, each one supporting a bus controller, bus monitor, RTSAs, and bus A and bus B. You can configure the bus monitor to record traffic to a specific set of RTSAs, or all RTSAs. You have the option of recording the data in binary or ASCII. You can customize the format of the output to suit your application. For instance, recording in CSV format to import into Excel. Lastly, you have the option to transmit the data. Here's a sample of the output. Please remember, you can quickly customize this output to suit your application requirements, such as removing some of this data or adding commas. So, there you have it, a complete and customizable 1553 bus monitor recorder that's flexible and ready to go.
And then let me just show you where that sample is. It's in our 1553 sample list. Lastly, we've talked about recording data, but let's consider sending the bus data out to external devices. We have two modes of operation. One is tethered to a PC and the program runs on the PC, or we have a fully standalone embedded mode. And we've written a package to assist you in transmitting data off the embedded product. Let's take a look at that.
Today we're demonstrating our wireless avionics capability by acting as a wireless access point. UEI supports all the major avionics protocols: A-Ring 429, MIL-STD-1553, 708, and A-Ring 664. As with all our I/O modules, be it a cube or a rack, you have the option to send the data out or receive data over UDP, TCP/IP, or WebSockets, via wired or wireless interfaces. You can also store the data locally if needed. How you interact with the system, either by PC, wireless device, or cellular device, is up to you. In this demonstration, we're publishing the first 5 words of the raw 1553 bus monitor data over Wi-Fi. The 5 FFF is the delay since the last word or message was received. The 4104 is the command word. The next 4 words are data words ordered with the delay since the last word was received. The 83 and 84 represent the delay between the last word and this word. And the A049, B049, C049, and D049 are the actual data words that came across the 1553 bus. The HTML page and the data that is published can be tailored very quickly to your particular application. So there you have it. Our flexible I/O system not only supports all major avionics protocols, it allows you to store and send the data the way you want, either wired or wirelessly.
So there are many ways to send data out. You can send it via sockets and UDP. We've also developed the PAC HMI that allows you to send data out WebSockets or TCP/IP to applications. It's a shared data protocol. And one more piece of code. This sample has every option to our bus monitor in it. If you need to configure a channel for an RTN bus monitor, here's the code. If you'd like a BC to have a bus monitor, here's the code. If you'd like a bus monitor only, and here are the 2 modes of operation. Raw mode is just this, and full message mode is here. And I've taken this code many times and just added it to applications I'm writing. So to recap, the bus monitor can be used standalone or together with a BC or RTSAs. We support a wide variety of programming languages and interfaces: C, C++, Python, LabVIEW, Simulink, and more. The bus monitor can help you debug traffic on the bus in many ways: by running a complete application on a loopback test adapter, by removing wiring and ensuring the application is asking the BC to send all required commands, or by using the raw mode to find any missing word in any message. You can easily record the data or transmit it out. Some questions have come in. Can I run 2 I/O boards and 4 bus monitors? Yes, that's absolutely possible and has been done. Is the bus monitor RT-based or RTSA-based? Well, it's both. There's a mode you can run it and record all the data from an RT, or you can filter down to particular RTSAs. Do you support direct coupling? Yes, we support direct coupling and transformer coupling. Can I monitor the bus and disable selective RTSAs based on certain commands seen? Yes, if you're using our I/O board for the RTSAs, you have full control of when an RTSA is enabled or disabled. Can you enable and disable each 1553 channel independently? Yes, there's sample code in sample 553 that shows you how to do this right here. Can you please elaborate on the dual redundancy implementation? There are 2 sides to the bus, and the bus controller will transmit on one side and look for a reply. If it gets a reply, it's all set. If it doesn't get the reply, it tries the other side of the bus and hopefully gets a reply there. If there's no reply at that point, it might mark the RT as disabled. That is standard 1553 protocol. Can I use the bus monitor to see bus controller traffic if they're on different channels? Yes, if you wire each channel to the same 1553 system. But internally on the I/O board, they're independent sections of the FPGA. Can I record bus monitor data without using the sample 553 recorder you mentioned? Yes, at any point you can simply write to a file, whether you're using C code, C++, LabVIEW. We provide that sample as a courtesy.
Okay, thank you, Phil. That was great. And thank you everyone for participating. We'll be sending out an email later on to all our webinar participants with a full list of videos and content we've referred to in this webinar. If you need any additional support or you've got suggestions for future webinar topics, please email us at support@ueidaq.com or call us at 508-921-4600. Looking forward, we'll be continuing our Masterclass series at the same time next Thursday. As you can see, May is Avionics Month, so we'll be focusing on ARINC 429, followed by 2 more classes on MIL-STD-1553. It's also worth mentioning that we record every webinar and post the video online the same day. You can watch any of our previous webinars either on our YouTube page or on our own webpage, ueidaq.com/videos. So that about wraps it up for this week. We hope you found this webinar useful and hope to see you again next week. Until then, please stay healthy.